Okay, class, good afternoon. So this is another topic in thermodynamics, the conservation of energy. So this topic is divided into presentations. Okay, so this conservation of energy is the so-called first law of thermodynamics. Okay, what does this law means? Okay, the law of conservation of energy states that the total amount of energy in an isolated system remains constant over time. So, so this law means that energy can change its location within the system and that it can change form within the system. For instance, chemical energy can become kinetic energy. Another is, say, potential energy become kinetic energy or change to kinetic energy and so on and so forth. So let us now come to the forms of energy. So actually, energy is divided into two parts. First is the so-called stored energy. So what is this stored energy means? Energy stored within the body which goes or dependent upon the flow of the mass. Okay, so what are those energy? First, we have the so-called potential energy designated as PE. Another is kinetic energy designated as KE. Another is internal energy designated as U, and the flow work or flow energy designated as W sub F. Okay. Another form of energy is the so-called transition energy. From the word transition or energy in transit or in motion. So which are not dependent upon the flow of the mass. And what are those energy? One is heat energy and another is the mechanical work or W. Okay? So let us discuss these forms of energy one by one. Okay? First is the potential energy. So this energy is due to the elevation of the body or the system. Okay? So the higher the change in elevation of the system, the higher the value of the potential energy. So potential energy rather depends on the elevation of the object or a system. Okay? So substituting now potential energy. So considering the illustration given on the slide. Okay? So we will notice that we have here potential energy at 2, which is at higher elevation, and potential energy at 1 at lower elevation. And the difference between the elevation between two positions is, of course, the delta Z or delta H. Okay? Or the change in elevation between two state points. Okay? So, substituting now, potential energy at position 1 is equals to mass multiplied by the gravitational acceleration multiplied by the height at point 1 divided by the constant of proportionality. Okay? So, determining now the potential energy at point 2, P sub 2 or P sub 2 is equals to M, the observed gravitational acceleration, multiplied by the elevation at point 2 divided by the constant of proportionality. Okay, so let us now analyze the unit of potential energy. Okay, so in SI unit, the mass is given in kilograms. And then, the gravitational acceleration, of course, is in meter per second square. And the change in elevation is in meters. Divided by the constant of proportionality, which is equivalent to 1 kilogram meter Newton second square. So, we will notice that the constant of proportionality here is unity. So, remembering the second law of Newton. And take note that the unit of the force here is in Newton and the unit of the mass is in kilograms. Okay, so substituting now the values and then eliminating units which are the same. The remaining unit now is in Newton meter or joules. Okay, so if we want to get the unit in kilojoules, of course, we divide this value by 1,000 to make it kilojoules. Okay? So, in English units, the change in potential energy. So, of course, the unit of mass in English is in pound mass. The gravitational acceleration is feet per second square. Okay? So, and then, of course, the change in elevation is in feet. Okay, so, the value, of course, of the constant of proportionality is not unity, since the value of force here is in pound force and the value of the mass is in pound mass. Take note, if the unit of the mass and the force are the same, the value of the constant of proportionality is not unity. Okay, so take note. So, the mechanical equivalent of heat. So, we have here 1 BTU or the 1 British thermal unit is equivalent to 778 foot-pound force. And 1 kilocalorie is equivalent to 428.1 kilogram force meter. Okay? So, let us now proceed to kinetic energy, designated as KE. So, kinetic energy is a stored energy of a body by virtue of its motion or velocity. Okay. So, let us consider this illustration below the slides. Okay. So, at this point 1, the body or the object has a velocity of v sub 1. And of course, it has a value of kinetic energy at point 1, since at point 1, the body is now moving. Okay. So, take note, if the velocity is 0 or the body is at rest, the kinetic energy is 0 also. Okay. So, starting now to move, the final velocity of v sub 2 at certain distance dx or differential x, the value of kinetic energy at this point, of course, is kinetic energy at 2. Okay? So, take note that the velocity could be ascending or descending motion. Okay? So, if the velocity is constant, meaning the change in kinetic energy is 0. Okay? So, let us now derive the equation, okay, for kinetic energy. So, the principle here is defining the kinetic energy equals to the work, okay, where F, the work is equals to F multiplied by dx and differential of Ke or change in Ke. Okay? So, integrating now the two differentials. So, where F is equals to mgo gc or the weight, F is equals to W is equals to mg. Okay? So, take note that GO is, of course, the observed gravitational acceleration and GC is the constant of proportionality. Okay? So, F now is equals to M multiplied by GC. Okay. So, GO can be written as the differential of dV over dt and then multiplying that by dx over dx. So, that is also equivalent to 1. So, it does not affect the equation. So, and then substituting it to the original equation, F now will become mgc. So, interchanging dx here. So, that is dv over dx multiplied by dx over dt, where dx over dt can also be equal to the velocity. Okay? So, where dv multiplied by the differential of the velocity with respect to the differential distance. Okay? So, integrating now. So, change in kinetic energy is equals to the integral of m over gc multiplied by the velocity and then multiplied by dv over dx. And limit from, of course, 1 to 2. Okay? So, from the previous illustration. Okay? So, change in kinetic energy now is equals to, so, m over gc, so, multiplied by b, so, plus 1, okay, divided by the exponent 1 plus 1, and then limit from b sub 1 to b sub 2. Or simply, the change in kinetic energy now is equal to 1/2 mv square, or the change or the square of the change in velocity. Okay? So let us now apply the previous formulas. Okay? So, taking now this example, okay, there are 400 kilogram per minute of water being handled by a pump. The depth is from 20 meters deep and the delivery velocity is 15 meter per second spine. The change in potential energy, kinetic energy, and the required power of the pumping unit Fg is equals to 9.75 meter per second square. Okay, so solving now the potential energy. So from the previous equation, change in potential energy equals to mg delta z. Okay? So take note, the mass, the gravitational acceleration, and the change in elevation. So substituting now the values, so 400 kilogram per minute, and then multiplied by 9.75 meter per second, square rather, and then multiplied by the change in elevation, which is 20 meters, divided by 1,000 to make it kilojoules. So therefore, the change in potential energy is 78 kilojoules per minute. Okay? So, it is clear. So let us now proceed to the change in kinetic energy. So knowing that change in kinetic energy equals to 1/2 mv square, and then substituting values, m is 400, the velocity is 15 square. Okay? So delivery velocity is 15 meters, minus 0 is 0. So multiplied by, okay, changing this to kilojoules, the equivalent value is 45 kilojoules per minute. Okay? So let us now calculate the power required. Okay? So the power required, of course, is the sum of those energy. So that is 78 divided by 60 to make it kilojoules per second. So plus 45 kilojoules per minute divided by 60 to make it kilojoules per minute. Therefore, the power required is equal to 2.050 kilowatts. So kilojoules per second is kilowatt. Okay? So I think it is clear to everybody. Okay, so let us take another example. A 600 kilogram hammer of a pile driver is lifted 2 meters above a piling head. What is the change of potential energy? If the hammer is released, what will be its velocity at the instant it strikes the piling? Okay, local gravity is 9.65 meter per seconds. Okay, solution again. Change in potential energy equals to mg delta Z, and then substituting the values. So that is now equivalent to 11.58 kilojoules. So this is the energy required. 11.58 kilojoules. Okay? So again, so as the file driver released, so that is mg, say again, changing the formula or changing the known values to the formula. So that is now equal to 11.58 kilojoules. Okay? So the velocity, of course, so will be equated from the equation, from a pre-pole equation. Okay? So rectilinear translation, where the square of the velocity final is equals to square of the velocity initial plus 2s. Okay? So you can also solve. Okay, so it is not, or it was not included in the on the slides. Okay, so it was omitted. Another, we have the so-called internal energy or stored energy due to its motion of molecules and forces of attraction between them. Okay, so the change in internal energy, of course, is an energy due to the change in temperature of the substance. Okay? So that is why, if we look at the equation delta U, that is equals to the mass of the substance multiplied by the specific heat at constant volume, since the volume of the substance here does not change. Okay? That's why we use CB. And then, the change in temperature between the initial and the final state. Okay? So, that is for internal energy. Okay? So, units of internal energy. So, in English, MKS, and SI. Okay? So, in English units, the internal energy is defined in the British thermal units. In MKS, that is defined in kilocalorie. In SI, that is joules or kilojoules. Okay? So, take note, the units of specific heat at constant volume. In English, the unit of CB is in foot-pound force per pound mass degree Rankine. In MKS, that is kilocalories per kilogram Kelvin. And in SI, kilojoules per kilogram Kelvin. Okay? So, another is the so-called enthalpy. So, enthalpy is a composite property applicable to fluids. Okay? So, wherein the enthalpy is the sum of the internal energy plus work. Okay? Where work can also be defined as the pressure multiplied by a volume. Okay? So, again, enthalpy is equals to U plus flow work. Delta H is delta U plus change in flow work. Knowing that delta H is equals to delta U, which is MCB delta T. And work is equals to PB, where PB is equal also to MR delta T. Okay, so here. So, delta H now is equals to M multiplied by CB plus R delta T. But CP is equals to CB plus R. Okay? So, therefore, delta H now is equals to MCP delta T. Okay? So, MCP delta T. Changing CB plus R by CP. Okay? So, units of enthalpy. Again, in English, that is BTU or the British thermal unit. In MKS, kilocalorie. And in SI, that is joules or kilojoules. Okay? Another is, we have also the so-called flow work. So, what is a flow work? Flow work is the energy required to move the fluid across the boundary of the system. So, this is a function of a pressure. Okay? A pressure. And of course, the volume or specific volume. Okay? So, let us now consider the illustration. So, we will notice that a mass will enter the system with a pressure and volume at 1. And will exit at mass. Of course, the mass doesn't change with a pressure of P sub 2 and B sub 2. So, getting now the flow work at 1, that is pressure multiplied by the specific volume at 1. Okay? And for 2, the flow work at 2, that is pressure at 2 multiplied by the volume at 2. Okay? So, changing now the getting now the change in flow work, that is equals to P2 B2 minus P sub 1 B sub 1. Excuse me. Another is heat. Heat is the energy crossing systems bounded because of temperature difference. Okay? So, temperature difference between the system and the surrounding. So, without any temperature differential between the body in the surroundings, of course, heat will not flow. Okay? So, that is why the heat is defined in terms of the change in temperature. Or, Q is equals to M multiplied by the specific heat and then change in temperature. Okay? So, English system defines the heat as BTU also. MKS, kilocalorie, and SI is in kilojoules or joules. Okay? Another is mechanical work. Okay? So, mechanical work is defined as the product of the displacement of the body and the component of the force in the direction of the displacement. Work is energy in transition. Okay? So that exists only when force is moving to a certain displacement. So without change in position, of course, there is no work develop. Okay? So where W is equals to force time a certain distance, or work is equals to P, or the integral of P multiplied by the differential volume. So this is for closed system. Okay? So of course, limit from the initial state points to a final state points. Take note that work is positive if it is done by the system. Okay. Done by the system. Example of this is a steam turbine. Okay? Steam turbine. Where the steam turbine, or the steam rather, enters the turbine at high pressure. Okay? So, and then, the turbine blade, of course, rotates, and the steam exits at low pressure. Okay? So, another is, work is negative if done on the system. So, take note. What example can you give to this? An example of this is a compressor. Okay, so a compressor will not run if there is no energy entering towards the compressor. Okay, so of course, the energy utilized towards the compressor is maybe an engine which drives the compressor, or maybe an electric motor which also drives the compressor. Okay? Another, we have heat. Okay. Heat is positive if added to the system. So, if considering a system, if heat is entering the system, that heat, or Q, not W, is positive. Okay? So, but if it is rejected or coming from the system, Q value is negative. Okay? So, I think it is clear. Thank you very much. So, that ends my presentation.